My name is Kaijin Lei. Today I will talk about permutation matrices and my solutions in CA3. Permutation is a way to change the order of elements. Matrices were developed in the 19th century by Kyle and Sylvester, and they were used to describe linear transformations. After matrices became common, it was natural to express a permutation as a matrix. The permutation matrix is a matrix that performs a reordering when we multiply it with a vector or another matrix. Our permutation matrix has a clear pattern. Each row has one entry that is 1, and each column has one entry that is 1. All other entries are 0. This pattern shows how the matrix moves each position to other place. When we multiply a permutation matrix on the left to of other matrix, it changes the order of the rows. When we multiply it on the right, it changes the order of the columns. The inverse of a permutation matrix is its transpose, because the transpose brings every position back to where it came from. This gives us a simple way to reorder data. A permutation matrix can show a simple swap. One example starts from the identity matrix I4. And then we swap row 1 and row 2. It looks like this. This matrix moves row 1 to row 2 and row 2 to row 1. We also have a matrix that swaps row 2 and row 3. It once appears in the positions that make this switch. This matrix keeps row 1 and row 4 the same. It only moves row 2 and row 3. These examples show how the ones and zeros mark the movement of each row and make the reordering clear. Permutation matrices can be used in many parts of linear algebra. They can swap or reorder rows when we solve linear systems, and they can reorder columns when we place them on the right of the matrix. They also help in computing because many tasks in the simple and direct way to move data to new positions. A permutation matrix is a square matrix with one entry equal to 1 in every row and every column, and all other entries are 0. This layout shows how the matrix moves each position when we use it. A square root of the identity matrix is a matrix that becomes the identity matrix when we multiply it by itself. So the matrix brings everything back to its original position after two steps. A proper square root is a matrix that follows this rule and is not the identity matrix. It has some movement in it, and it doesn't leave everything fixed. This notation tells us how many proper permutation matrices of size n square to the identity matrix. This gives a simple way to describe the number of proper square roots for each size. The permutation matrix matches a permutation of the numbers from 1 to n. One matrix squared gives the identity matrix. The permutation can only have one circle and two circles, because no longer circles doesn't bring every element back in two steps. A one circle is a fixed point, and a two circle is a swap of two elements. A proper square root needs at least one swap, so it must contain at least one two circle. If a permutation has k swaps, then 2k elements are involved. We choose these 2k elements, and then pair of them to form the k swaps. This gives a clear idea of how the counting method works. To form the final formula, we look at how many swaps a permutation can have. We choose these two k elements, and this gives the binomial term. Then we set these two k elements into k unordered pairs, which gives the pairing term. When we multiply these two parts, we get the number of permutations that have exactly k swaps. A probable square root must have at least one swap. So we start at k equal to 1. We add all the terms up to the largest possible value of k. This sum gives the total number of purple permutation matrix that square to the identity. My program takes a number of n as input. This number is the size of matrix. The program gets one number as output. This number is squared n. It tells us how many purple permutation matrix of this size squared to the identity matrix. In the code, n means the matrix size. The variable k is the number of swaps in the permutation. The variable total stores the sum. Each time the code finds a new value for a given k, it adds it to total. At the end, total is the answer that the program prints. In this presentation, I talked about permutation matrices and how they change the order of rows or columns. Explained a proper square root of the identity is a permutation matrix built from fixed points and swaps. I showed how we can count all of these matrices using CA4 formula. I also explained that my code follows this formula and computes the number of squared n for each matrix size. Thank you.